This episode of Overview Biostatistics will bring you to a closer look at the statistical concepts where in the previous slide I emphasized about we need to quantify what was found in the sample to what would be found in the populations, which is called statistical inference. But how can we sure that what would be found in the populations will be correct, will be valid by this method? So we need to know how to deal that. How can we quantify things that are varying? So whatever it is, if we know its pattern, we can predict it, right? If the pattern is stable, it's easy to predict because it will be the same as the previous one. For example, the temperature of this city is the same all the whole year, so we know what is the temperature in May, for example. Or if we know the patterns that increase from January to December, every month increase for 1 degree Celsius, for example, we know that what would be the temperature in May, the same thing. So the pattern will be the key to know the answer. Even we don't have the data at the point that we want to know. That means in the population we don't have that, but we will have from the sample. So the pattern of the data, actually the data distribution. So if we know how the data of the sample distributed, the same way we will know how to use it in the populations. So is there any type of data distributions that we can rely on because things are varying? The answer is yes, luckily for humankind. Let's walk together. So when we touch the variability, rather than just quantify it, we then, another way is to visualize it. The previous slide I show you this one, which is this one, visualize it in the histogram in the bar like this. Actually it's the area. So to be more understandable, we draw the curve that still maintain the area under the curve as the area of the whole curve of the histogram. Like this one, get rid of it, we add this because we get rid of this, something like that, or even like this. So this is called frequency curve. The frequency curve maintain the area under the curve of the histograms. Okay, so if now we put only the area under the curve, just like this, it can then be easily to see this is a highly skewed data where many observations are in the low value, but some are in a very high value. For example, this is how we describe it. This is right skew, and this is symmetrical curve, like a bell shape. So the area under the curve and the characteristics of the curve tell us about how the data is distributed. It's skew or symmetry, and how variations of it, wide or narrow, of the base of the graph. And we take the median, the mean, it will be like this. So, but the median is about somewhere here where it's divided the data to have 50% lower and higher. But if it is symmetry, mean and median will be the same. Therefore, if we want to know if the data set that we are dealing with is skew or symmetry, we can just look at the mean and median. If it is close together, it is symmetry, for example. So it tells us a lot about the frequency curve. We will see a lot like this in statistics book. Now, what we will rely on for statistics is called central limit theorem. It is nothing. It is just some natural phenomenon again that we really touch something that is really true, and then we can rely on what is known to be true. So first, what is happening in our practical way when we doing a research? We collect the raw data, and here, for example, the data set that is highly skewed and skewed to the right. It's just like the distributions of the income in developing country where many people are poor, I mean low income, some very rich up here. The income data again, if it is distributed like this, that means a few people poor, a few people rich, most are in the middle class, for example. This is symmetrical. Now, if it's like this, that means a few people, few proportions of people are poor. Most of them are rich, things like that. We want our country like this. So here is the raw data obtained from each individual and plot in the distributions and displayed by the curve, frequency curve. So as you can see, this one is the X bar. So each point here is X, or a single data point. A summary is X bar, or mean. Now, if we take a random sampling several times, mean repeated sampling, like doing the first sample, like a survey of income for 100 people, we get X bar 1. Do another researcher do it again, a survey for income survey, and gets X bar 2. The last researcher get X bar 3. We repeat a lot of study, mean repeated sample, and take the X bar to plot. This is called the distributions of the statistic. Here is the statistic, describe the sample. So this is the distribution of statistics. It will always distributed in the bell shape, or symmetry, no matter how raw data is distributed. But the sampling mean will distributed symmetrical, like this, like a bell shape, or sometimes we call normal distributions. But in fact, we cannot say it's normal distribution yet, because when we say normal distribution, it need to be complied with some definition. So here we will say symmetrical first. This is the first truth that we can test anywhere. We will get the same thing. Okay, we can rely on some truth now. Okay, that's the first one. The second one that I like to say to you is that if the data of the population is distributed, like for example, the income in the developing country usually distributed like this, the right scale. When we repeated the sample, we will always most likely to get the distributions of the data, the raw data, that similar to the parents' population. Okay, the daughter distributions mean the sample will distributed the same way as the parents mostly, but a few will get the distribution differ from the parents like this or like this. It can be, but very unlikely. Therefore, if the data of the populations like income is skewed like this, no matter how you increase the sample size, how large the sample size it is, it will always similar, most likely, not always, most likely similar to their parents. Cannot be symmetry, but some could be. Therefore, we cannot rely on the distributions of the raw data for any inference. But the distribution of the sampling mean will always like this. We can then rely on this. So don't confuse with some understanding that if you increase the sample size, the raw data will distribute it normally. It's almost impossible if the data of the population is skewed. Okay, now this is again the distribution of raw data. I emphasized it. This is the distributions of the sampling mean. Now, distributions of the raw data to get the distributions of the sampling mean, you need to do a repeated sample to get like this. And if the sample is large enough, that symmetrical distributions will follow a theoretical distribution called normal distribution. Okay? So from the sample, we have, if we do a repeated sample, we have many X in one sample, but one X bar and one SD. If we do a repeated sample, we have many X bar. If we take many X bar to plot, it will be like this, to get many X bar. And in the middle, X bar of the X bar will closer to the parameter mean, or called mu, in the population, as if we ask or we survey for every individual of the population. Now, take a look at the variations of the data. In raw data, we call standard deviation. But the standard deviations of the distributions of the X bar, we call standard error. Okay, so remember about this, that this is SD is for raw data, SE is for repeated sample, or the variation of sampling mean. Now, in a large sample, we need to have a standard normal distribution so that we can use for the inference. Therefore, the mean we take 0, and each one point of this away from the mean is the number of standard deviations. Okay. And how? When we in practical, we just do only one study. We don't do repeated study. How can we get the SE so that we can use this property for the inference? Luckily that the standard error or standard deviations of the sampling mean, we can estimate from the one studied standard deviation here, we do only once, by taking that standard deviation divided by the square root n. Okay, so this also we can do an experiment that we simulate a very large data and take it as the populations, and then we draw a repeated sample, and then we can see this. We don't have much time to touch, but when we meet in the class, we will do that in the stat village of the school, of the faculty. So this is possible now to use only one study so that we can know in the larger population by this. And the normal distributions is the theoretical distributions where we can get the value in the graph. Every one standard deviations segment in area under the curve have how many percentage of the whole curve, and this is the formula, one of the formula that changed the world, like this. Okay. Then we have the properties of the normal distributions like this, the theoretical distributions. So I put it here about area under the normal distribution curve by put 5 rows here. As I said that the normal distribution has its own properties where we substitute the number of y in here, and it will show about in the middle it is the x bar or the mean, and the area from the mean to be 1 standard deviation plus or minus 1 standard deviation cover the area about 68.26% of the whole. The whole is 100, and plus or minus 2 cover the area about 95.45% of the whole, at plus or minus 3 standard deviation cover the area about 99.73%. So this is a brief summary of the normal distribution properties. Therefore, in number 1, where I set x bar here, that means the curve is from raw data, where the middle is x bar, raw data of the sample, and x bar plus or minus standard deviation 1, 2, 3 here. It's almost impossible that the raw data follow the normal distributions like this percentage. Mean you compare the observed data with the theoretical data, if it fall into this percentage like this. Actually, we have smaller segment to compare for that. So I can say it's almost impossible that the raw data follow normal distributions. Therefore, I encourage people not to say the raw data have normal distribution. It's impossible. Okay. It's different in some way. We can just say it's symmetry so that we can accept the mean to be used for the inference, for example. So the first row is from one study, it's impossible to follow normal distribution. The second row, where the middle I put mu, that means it's also the raw data, but take all, not sample, all individual of the population or census. The row number 2 also impossible that the raw data will follow normal distributions. For example, the distributions of income in the developing country. Even you take the sample or the whole population, cannot be symmetric. It always skew, for example. Okay, the third one, I put x bar of the x bar in the middle. What does it mean? It means we use the x sampling mean as the data to plot the distributions. That means the data to plot this is from the summary of the repeated sample or sampling mean. This is what we have touched so far, that the only one that can happen if the sample size is large enough. That is why we need to calculate the sample size to be sufficient or large enough when we do a study. So we can rely on only number 3 because it is always true, no matter how raw data is distributed. All right. If you did not believe up to now, we will find time to touch it, to experiment it, to prove it later. And then the fourth row, I put it here, is just the number of standard deviation or sigma, standard error, whatever here. So this is, you see, it's a coefficient that correspond to the percentage here. It's the number of times of the deviations from the mean, you know. So we use this, sometimes we call z-score if we use this one as the normal. In other distributions, this might be differ according to the distributions. For example, t-score, t-test, f-test, chi-square test, whatever, it's not the normal in other case that I said. But it is the coefficients that correspond to the percentage of the area under the curve. This will be used as the probability of obtaining this value or the subjects under that conditions to understand, to interpret, to answer the research question. Now, I put the number 5 for the example that I will show you in the next slide. Okay. About if we draw a sample size with n of 25, that means the sample. Of course, it's just like the row number 1 because this is a raw data. It will not follow like that. So for example, if I put here 52, that means the mean is 52. If I put here the 57, that means the standard deviation is what? 5, right? So if the raw data follow this distribution, we will have 68.22 subjects of the 25 that have the weight between 47 to 57, which is almost impossible. So that is why raw data almost cannot say it's normal distributed, but just say symmetrical or bell-shaped. Okay, so this is the first one I like to show you. And then we use this one as the coefficients to correspond to that. If plus or minus 3, that means this area, which correspond to 99.73 of the area under the curve. If we use plus or minus 2, and it is in this area, it corresponds to 95.45 area under the curve, and plus or minus 1 is about 68.26% of the area under the curve. But it's quite difficult to get the probability, say like 0.9973. Therefore, we need an easier number for further use. So we reduce to be, if we want 0.99 only, so the remaining probability is 0.01. This is called the alpha. If we consider area less than that, about 0.95 rather than 0.9545, it corresponds to an alpha of 0.05 and 90, not 70, not D. So this three common number is used in statistics, like 99% confidence interval, 95%, 90%, not 68 like that. Okay, so it's just about the preference for easily interpretations or communications only. Okay, this will be used in future. So that's for this episode. I like to show you where this understanding will be the fundamental for everything in statistics. When we do in practical way, we just touch the data by doing data collections in one sample. For example, here, one study with the sample size of 25, measure the weight, we get X bar of 52, and calculate for standard deviations of 5. We use this to inference to the populations where we draw the sample from, so that we know that in the populations, how likely the weight will be. We will see in details the next episode about population parameters. It is the statistical inference.